Hello, welcome back. I think in the last class, um, Dr. Danda has spoken about least square optimization and how the linear concepts, concepts in linear algebra could be used to solve some practical problems in image processing. So today, what I'm going to do is I'm going to extend his lecture by working out principle of the least square optimization. And also, if you recall, on Monday, I did say that the projection, the idea of projection, right, is quite useful not only in the context of creating an orthonormal basis, but also from the context of finding the optimal distances between a point and a line and so on and so forth. Right? I mean, this is a very, very useful concept in the sense that let me first give an example from neural networks. Okay, I mean, I think all of you are familiar with neural networks, right? I mean, is there anyone here who is not familiar with how neural networks work? Yeah, I mean, you can raise your hand if you're not, but I mean, I'm assuming that all of you here are familiar with neural networks. Okay, so I mean, if you think of an activation function, right? I mean, and probably so let me first write. Okay, so let me ask you a question. Let's say I give you two cars, right? I mean, in a two-dimensional space, right? I mean, how would you figure out if the two cars are close to each other or not? Guys, how would you figure out if the two cars are close to each other or not? I mean, let's say I give you a straight line and I give you a circle, right? And I know that possibly, I mean, there are, I mean, very few points of intersection between the two curves, or maybe there is none. I mean, the two curves never intersect, right? I mean, in such a scenario, how would you, I mean, if you are asked to comment on the proximity of the two curves, I mean, how are you going to, solve that problem? What would be your approach? Pawan?
Yes.
Yeah. Did you get my question?
Yes, sir.
Okay. So what do you think?
Let's say, I mean, we can take some of the points on one curve and project them onto the other curve and see, I mean, the distance of those points.
Right. I mean, so, right. So, but I mean, you cannot do it for some of the points because then if you only do it for some of the points, then the choice of those points could be questioned, right? So what you have to do is that you have to, compute some distance between the two curves for all values of the independent variable, right? Okay. So, I mean, it has to be an optimization problem in the sense that you are actually optimizing over the entire all the values of the independent variable in its domain, correct? Okay. So there is some distance that you need to compute, correct? Okay. So, I mean, and there are several such distances, like there is Hausdorff distance, there is Euclidean distance, and then there is distance in the least squares, right? Okay. Now, let me, give you that example from the neural network, right? I mean, so you know the activation functions are used to trigger neurons in the sense that there would be some threshold below which the neurons are inactive, and you have to trigger them so that the function value or the output value crosses that threshold, and so that the neuron triggers and the connection is established between neurons between the layers, right? I mean, in the input layer and the hidden layer and the hidden layer and the output layer, right? So activation functions do play a role. I mean, a very standard activation function is the logistic function of the sigmoid function, right? And then there are some problems in that sigmoid function in the sense that it could have a vanishing gradient problem, right? Or it could sometimes lead to a flat loss function, because the sigmoid is sort of tapers off at the end, right? So in order to encounter these, I mean, our activation function was proposed some time back, which is called a ReLU, which is a rectified linear unit, right? Okay. Now, how does the rectified linear unit look? The rectified linear unit, it looks like this, right? I mean, the plain old vanilla version of the rectified neural network unit looks like this, right? It's so basically a strictly monotone function when your x values are positive, and then for all negative values of x, your output returns 0, right? I mean, it obviously has a problem, but unlike the sigmoid activation function, this is like strictly monotone for positive inputs, right? Okay, so now, but ReLU also has its problems. So the problem is that here at this particular point, which is at x is equal to 0, it has a singularity. In the sense that the derivative is undefined here. You cannot. But I mean, why do I care? Why do we care? Because if you recall the backpropagation process where you update the loss function with respect to the error, you need to compute a bunch of derivatives, right? Which is you backpropagate the error from the output layer to the hidden layer, from the hidden layer to the input layer, right? Each and every time you go to update each of the weights that you have assigned, which you are going to use to connect the neurons from different layers, correct? So what happens is, if you do this process carefully, you will see that somewhere the derivative of the activation function is used, right? So if you are passing through the point x is equal to 0, which could be the case, and at that point your derivative is undefined, you have a problem, right? Okay. So in order to mitigate this problem, a bunch of different variants of ReLU have been proposed, right? One is a leaky ReLU, one is like, for example, let me write. I mean, so in order to mitigate this problem, right? Leaky ReLU, right? And then exponential ReLU, right? And so these are sort of more continuous versions of the ReLU activation, in the sense that it tries to solve this singularity problem at x is equal to 0 by defining something else. And then there is this activation function called swish, which is from the stable of Google Brain. And then recently, in a British conference on computer vision, there is a guy from India who proposed this activation function mesh, okay, which is also a continuous variant of ReLU. But what mesh does is, unlike ReLU, it is not monotone. Okay, I mean, that's a different thing to talk about, why activation functions need to be monotone, or is there a necessary and sufficient condition for the activation functions to be monotone? I mean, I don't think so. In fact, very recently I have a paper where I showed that you don't need the monotonicity property of activation functions everywhere, right? But imagine something more simpler, which is called a-ReLU or approximate ReLU. So what basically could be done is, all of these guys, what they are doing is they are trying to figure out some form of a smoother version of ReLU. These are all some sort of a smoother version of ReLU. Okay. All right. And this guy also does this precisely, right? But what it does is instead of sort of using a linear function, which ReLU does in this particular domain of X, what it does, it's defined in the following manner, that this is okay. And by virtue of defining a polynomial function like this, you actually eliminate the possibility that you would actually have a singularity here. So it's like sort of a really smooth version of this, right? Something like that. Okay. But I mean, you notice that when k is equal to 1 and n is equal to 1, this is nothing but the ReLU itself, right? But I mean, k and n could be other values other than k and n equal to 1. So in general, you could have something like this or something like this, something like more fatter, right? Okay. Now there is a question that how do I know the values of k and n, right? Okay, so that now the most decent thing to do, okay, and most scientifically accurate thing to do, in my opinion, is the following: that you should not be losing the good properties of ReLU, right? So by defining the function this way, I ensure that for positive values of X, I retain the monotonicity, strictly monotone property of ReLU, right? And by defining the function this way, by introducing a polynomial, I ensure that the singularity is removed, right? But what else do I need to ensure? I need to ensure that because ReLU in practice works very well, right? So what I need to ensure is that this particular activation function that we proposed, right, also remains close to ReLU, okay, for all values of X. So pretty much, in order to replicate the good properties of ReLU, what we are looking at is to minimize the distance between okay, and it turns out over all values of X, this is an optimization problem. This is an optimization problem where there are some constraints, and these constraints are that you make sure that k is, I mean, you set a constraint that X is positive, you set another constraint that k is also positive, and you set a constraint that n is greater than 1, right? You also set another constraint that k is also greater than 1, so that you don't end up actually copying the same ReLU function, right? So it's basically a constraint optimization problem, okay? The constraint optimization problem, which you can solve using the least square optimization technique. Okay, so therefore, what happens is, if you solve this constraint optimization problem, it will return you a range of values for k and n, for which the distance between the least square distance between ReLU and AReLU would be the smallest, right? And then while training your neural network, you go back and use those values of k and n instead of tuning k and n for every iteration. So pretty much what least square optimization solution does for us is to get rid of the hyperparameter tuning process, which is a very, very expensive process and incurs a lot of overhead. Okay, so this is one of the another useful application of least square optimization. But having said that, okay, so no need to tune. So that is one of the incentives of doing a least square optimization in the context of this. Okay, all right. Now, having said that, let's come back to a very simple but practical problem. I mean, because I imagine that a simple demonstration through an exercise was not done in the last class, right? So let's try to do this first. I mean, let's try to give another motivation of solving or using a least square optimization technique, and then I will work up a little bit of theory of it. Okay, so let's say I have 3 straight lines. Okay, all right, and these straight lines are the following. Now, I'll just write this in the y equal to mx plus c form for each one of these guys. So this is, and this is, right, and then this one is easy. Okay. Now, if I ask you to solve this, basically, solving a system of equations using a matrix solver. So you can pretty much write this in the form of Ax equal to b and see if the matrix is full rank, and therefore if the matrix is full rank, you can use an inverse or something else, right? And this is a three. I mean, it's like you have three equations and you have two unknowns. So technically, you should have no difficulty in solving this system, right? Okay. However, if I look at the picture, right? Somewhere over here. Okay. Okay. So I think you could figure out the several coordinates, right? Okay. So this guy uh, is okay, and okay. So this one is y equal to minus 1 half x plus 1 half, and then there is this guy. Okay. Um, which is Now, if you really think about it, I have messed up the figure, I mean, which I always you know end up to do. You will see that these three straight lines do not have a mutual point of intersection. Okay, so it's like there is no mutual point of intersection. No mutual point of intersection. So when you are asking someone to solve this system, what you are looking for is actually a point of intersection, right? I mean, that is the geometric significance of solving this system of linear equations. Now, if you know by visual inspection that there is no mutual point of intersection, right? So you are in no position to solve the system. Now, let's assume that somewhere over here, like somewhere over here. So, I mean, if you don't have an exact point of intersection, what is your next best guess? Your next best guess is that you think that there is some approximate point from which the distance of all of these three straight lines are sort of small, right? And that would be somewhere over here. Let's say this is some x star, right? Which is not the exact solution to the system, but it's somewhere in the 2D space, right? Which is really, really close to all of these straight lines. Okay, and your job is to find this guy. Okay, all right. So this is the motivation of the least square optimization technique, right? One of the strong motivations, because you know most of the linear algebra stuff that evolved is actually motivated by this, burning desire that, I mean, I have a large system of equations, and how should I solve this? Okay, all right. So let's, frame this up in the context of linear algebra, right? Okay. So let me first save this. All right. This should be 26. All right. So, so let's think about this, right? Okay. So let's go back to the theory. Now, what it does is, this is what I intend to do. I intend to solve a system, right? Okay, which is your typically an n by k, right? Okay, and x is a column vector, right? Okay, and you expect the coefficient, right, on the right hand side to be a column vector in Rn. Okay, now when there exists no solution to this system, when there exists no solution to Ax equal to B, right, this implies that you have the following, right? I mean, I have a column space which contains all my columns, right? Okay, A1 through AK, right? So these are column vectors with n rows, right? That is how it becomes n by k, right? And then I have this x1, x2, all the way up to xk, right? So that this is a k by 1. So you have an n by k and a k by 1. And what you get is an n by 1. Okay. In other words, what we are trying to do is that this A1, so I'll just use the vector notation just to, distinguish between A1 as a scalar and A1 as a vector. So this is just a column vector, right? So this is A1 x1 plus A2 x2, right, plus AK xk equal to B. Okay, so this is a linear combination of your vectors in the span of it, right? So if there is no solution, then what this implies is that no linear combination of columns of A, correct? No linear combination of columns of A equals, okay? This implies that B does not belong to the column space of A. Clearly, okay, all right. So now the point is, so therefore there is no exact X, right? So therefore this implies that there does not exist an exact X such that Ax equal to, okay, all right. Now, but however, what if there exists an approximate X? Okay, let's call this X star thing. Okay, all right, for which this Ax equal to B such that Ax equal to B. So in other words, if we cannot solve AX equal to B, can we solve AX star equal to B? You recall that on Monday's class, while talking about orthogonal basis and orthogonalization, orthonormalization process, I did mention the sort of a projection matrix, right? And I also said that the projection matrix is a nasty one. Okay, it involves matrix and the transpose and its inverse and blah blah blah. So there has to be a way to sort of efficiently compute this, okay, without having to invert a very nasty large matrix. So the idea is this, that I have this column space of A. Okay, all right. So let's say I have this column space of A. Okay, and there, what I intend to do is the following: is that there is some vector, right? Okay, and this AX star is in this. I claim that X star solves AX equal to B, so therefore AX star is actually in the column space of A, right? But I also know that B is not in the column space of A, correct? So B is somewhere over here, right? It does not belong to the column space of A. But if B does not belong to the column space of A, as Pawan rightly pointed out, that we could have a projection of that, vector, right, in the direction of AX star, okay? That could be something like this, right? So what is this? This is nothing but, as we have seen in the Gram-Schmidt orthonormalization process. So this is a projection of the vector B in the direction of the column space, back to the column space of B. Okay, so we got to figure this out, right? Now this implies, this clearly implies that in order to solve this problem, this clearly implies that what I'm trying to do is that I cannot minimize. So also, solving AX equal to B implies that what you are trying to do is minimize the distance between B and AX. Now, what we hope is that if this minimum distance becomes 0, then X is called an exact solution to the system, right? So we are going to borrow that concept and rewrite here is that instead of X, because we now know there is no such X, what we can do is that we can minimize the distance between B and AX star, right? Okay, which means that you write a bunch of this, right? So this is actually B1 minus AX star 1, B2 minus AX2 star, so on and so forth, right? And essentially Bn minus AXn, okay, wrapped around the L2 norm, okay? So in other words, what you are trying to do, and this is a least squared distance, right? You are looking at you are squaring up the distances and taking the sum of all of that. So this is nothing but B1 minus AX1 star squared plus B2 minus AX2 star squared plus Bn minus AX2 star squared. So all values of X, right? Okay, you have to minimize over all values of X. So this is, since we are, this L2 norm is nothing but the squared sum of the square of the distances. That is why this kind of optimization technique is known as the least square. Okay. So therefore, having said that, what I do is I'm not exactly computing the exact solution. So what I'm doing is that I am actually coming up with a least square estimate for the system AX equal to. Okay, so this implies that what I'm trying to find is the closest vector. What I'm trying to find is the closest vector to the subspace, right? And this also implies that I'm projecting B onto the column space of, okay, all right. Now this, in turn, what this means is that what you are looking for, which is your AX star, which you are trying to approximate, right? Your AX star is nothing but that projection, correct? Okay, your AX star is nothing but the projection of B onto your column space of A, correct? Okay, so now the question is there an easy way? Is there an easy way to find this X star? Okay, so is there an easy way to find X star? So here all your concepts of linear algebra will come into play. Is there an easy way to find X star? Okay, so we'll see that in the next piece of work. Okay, so I'm going to redraw this picture again, which I don't mind doing. Is that let me first. So this is my projection X star B, which does not belong to the column space of A. So therefore, what you need to do is that you need to do this projection of B onto the column space of A, right? And this is nothing but you are projecting B in the direction of AX star. You have to do that, right? Okay, and you are sort of doing it. So you say that so therefore this is AX star. It's actually in the column space of A, right? Okay, and B is not in the column space of A. Now, I mean, what I can see is that what is your AX star minus B? What is your AX star minus B, right? I mean, AX star minus B is this, right? Okay. Now, this AX star minus B is nothing but the projection of B in the direction of the column space minus B, right? Okay. Now, this actually, and this projection is orthogonal. I mean, it may be apparent, may not be apparent from the way I drew it, but this is just you have to drop a perpendicular, right? So this is orthogonal to what? This is orthogonal to your column space, right? This is orthogonal to your column space. It has to be orthogonal to your column space, right? And so therefore, what happens is when I look at this guy is nothing but, it does not belong to the column space of A, but it belongs to the orthogonal complement of the column space of A. So you know from the idea of orthogonal complements of subspaces that anything that does not belong to a subspace has to belong to it, you know, orthogonal complement, right? If we are able to split the vector space into two subspaces. Now, what this means that the column space, the orthogonal complement of the column space of A is nothing but the null space of A complement. Okay, all right. And this is a standard theorem that I don't have the time to explain, but just trust me on this. Okay, all right. So these two are equivalent. These two are equivalent vector spaces. So what that means is this guy AX star minus B, which is orthogonal to the column space of A by construction, has to belong to null space of A complement orthogonal, right? So what that implies is that straightforward now, AX star minus B is in here, okay? And therefore, now this is this is nothing but the transpose, right? So what we can write is this implies that A transpose of AX star minus B belongs to the null space of A. Okay, and that means that A transpose AX star minus B is equal to 0, right? Because X star is such a vector which belongs to the null space of A. Okay, all right. So if I work this out, this is what I get, is that A transpose A X star minus A transpose B is equal to 0, and therefore A transpose A X star is nothing but A transpose B, right? And this is the least square estimate, okay? Least square estimate or solution to what? Solution to AX equal to, okay? All right. And if you want to write this explicitly, this will not be nothing but A transpose A inverse A transpose, right? Okay. And this is called pseudo inverse. Okay. All right. So it's not in a normal circumstance, your X star or your X would be A inverse B, straightforward. But here that inverse is undefined, right? Because that your column vectors, I mean, your B vector does not belong to the column space of A. And so therefore you have to do something like this, okay? Using the concept of orthogonal complements. Okay. So now having said that, so let's see how we are able to use this to solve the problem that we were trying to solve. Okay, so let's now go back to the problem. So what we will do is that we will go back to the example where we had this thing, right? We had, if you recall, let me write it here, 2x minus y equal to 2, x plus 2y equal to 1, and x plus y equal to 4. Okay, and so we have the coefficient matrix. If you want to write it in the form of ax equal to b, we have the coefficient matrix, which is 2 minus 1, 1, 2, and 1 and 1, right? Times x, y, and that is nothing but 2, 1, and 4. Okay, so this is your B, which does not belong to the column space of A, and this is your A matrix. So apparently this does not have a solution, right? Okay, but you know now what is A and what is B. Okay, so what you can do is that you compute this A transpose AX. Okay, so you know what is your A, so therefore you know what is your A transpose, right? So if you compute and you know what is your X, I mean, or X star. So now it is going to be X star, right? I mean, so this is X star and Y star, right? Okay. So if you do this A transpose A X star computation, right? Okay. So what you are going to get is 6, 1, and 1, 6 times X star, Y star, right? And that is equal to you know, whatever it is, and then you have this A transpose A, yeah, A transpose A X star equal to A transpose B, right? So you have your B matrix, which is 2, 1, 4, and then you have your A transpose matrix, right? So if you multiply A transpose with B, what you are going to get is 9 and 4. So this is your A transpose. Okay, all right. You solve this, and you will obtain your X star. And that is, I'm just keeping this step, I'm just straight away writing the solution, is that 10 over 7 and 3 over 7. Okay, So this is your approximate solution. So even though you know that those straight lines do not intersect and therefore does not admit of an exact analytical solution, using the least square optimization technique, you are still able to come up with an approximate solution. Now, let's see how good this solution is. I mean, so because if you have done it sort of right, then your ax star minus b, which is the distance between that approximate point from any of these straight lines, right, will be what? Will be the norm distance of all of these individual components, right? Okay. So you do this ax star because now you know your x star and you know your a. So you compute this, you multiply this, right? And you will get a column vector. So a is a 3 by 2 and x star is a 2 by 1. So you are going to get a 3 by 1, right? And b is also a 3 by 1. So this is what you are going to get if you do this correct, is that it's 17 by 7, right? 16 by 7 and 13 by 7, right? Minus your original b, which is 2, 1, and 4, right? You compute the least square distance of all of that. So this will be nothing but, 3 by 7 square plus 9 over 7 square plus 16 over 7 square. Sum of the square distances, right? And then you will take the square root, right? Okay. So when you take the square root of it, so eventually your distance would be, which is, I'll just once again write this straight away, 315549. So this is approximately square root of 6, right? I mean, approximately. I mean, so, and this is like what, 2 point something? I mean, square root of 6 would be 2.4 approximately. Okay. So the point that you have chosen, to be your approximate solution is at this sort of a distance from all of these points. Okay. All right. So this is how you actually work out a least square example, right? Okay. And this is how for all practical purposes, this is how the least square distance computation works. Okay. All right. So I'll just go to another example. So sometimes, even very complex fitting problems are solved using least square examples. I mean, least square optimization method. So such an example is the following. Is that, just think about this. I'll just, help you set up the problem first. Okay. So just think about this. You don't have to turn this in. The problem is the following. Can you find a line? Can you find a line y equal to mx plus b such that it fits these points? -1, 0, 0, 1, 1, 2, and 2, 1. Okay, so just before doing anything, just look at the scatter. So look at the scatter of these points. Okay, so if I draw this up, -1, 0 is somewhere over here, right? 0, 1 is somewhere over here. So this is fine. So you can see that at least through these 2 points, I can fit a line, no difficulty. And then I have 1, 2, so somewhere over here, right? 1, 2 is somewhere over here. And then there is a 2, 1. So you can now see the problem, right? I mean, how can you actually fit a line through all of these 4 points, right? Sort of, I mean, impossible, right? I mean, but what you can do is, I mean, using several trials and errors, I mean, on visual inspection, you can come up with a line which is sort of a good, and this is, you can think of this as a regression problem. This is nothing but a regression problem. Okay, this is nothing but a regression problem. And in the regression problem, this is what you do, right? I mean, you try to linear regression problem, you try to come up with a line, okay, which sort of fits most of the problems. You cannot ever find a line which will go through all of these points, because then it will be a perfect fit. However, if you do a polynomial sort of a regression or polynomial fit, you can actually sort of draw up something like this. You can actually sort of draw up something like this, which is this. Then it's a perfect fit. But in the real world, I mean, perfect fit is usually not solicited. Can you tell me why? So this is a machine learning question. Roshishnu? Yes, overfitting, right? Good. So, I mean, if you because the moment you use something like a nonlinear curve, the degree of fit is 2 or higher, right? So higher a degree of fit, it probably fits your training data points well. But if a new data point comes, the cost of such bias, because this is really what you are doing is a bias, right? I mean, you are fitting your bias. So the cost of such bias will actually lead to a very large variance, right? And this is called the bias variance trade-off. So I should be happy with a linear fit, right? Okay. So not a polynomial fit. A linear one. So how do we solve this problem using least squares? Okay. So what I can do is, I mean, I can just plug in these values, right? I can just plug in these values. And if I do that, I have an m minus 1 plus b equal to 0. And then I have m times 0 plus b equal to 1. And then I have an m times 1 plus b equal to 2. And then I have an m times 2 plus b equal to 1, right? Translate this to a linear system, okay, where your unknowns are m and b, right? It's minus 1, 1, 0, 1, 1, 1, and then 2, and 1, right? Okay, so this is your A, this is your X, this is your B. Now, clearly, there is no such combination of X. There is no such X, clearly, right? I mean, clearly, there does not exist any such X such that this AX equal to B holds, right? So therefore, you have to find an X star, okay? You have to find an X star, and that is nothing but your least square estimate. Okay, all right. So if it's a two-dimensional thing, I can just simply use linear algebra. If it's multi-dimensional, you know what, I have to use the gradient descent and all that, right? But I mean, so therefore what happens is this particular solution is nothing but the least square estimate, by virtue of which you would be able to figure out a sort of an acceptable value of m and b such that you are able to get a good fit. Okay, so that your least square distance is an optimum. Okay, all right. So with this, we sort of conclude the discussion on chapter 6, which is inner product spaces, orthonormality, orthonormal basis, and applications of orthonormal basis. Okay, all right. And the next thing that I'm planning to cover is, by the way, so you are familiar with, let me ask a question so that I won't bother, because most of you are in Ashwin's class, right? So you're familiar with the least square distance. I mean, you're familiar with regression problems, right? Both simple linear regression problem and multiple linear regression problem. Yes? Yes. So therefore, I won't bother. And do you understand the connection now between the linear algebra concepts and multiple linear regression problems? Okay, okay, Aditya. Okay. So what I will do is in the next class, what I will do is I will give you very okay, all right. Okay, okay, all right. So I'll address this question because this is also a very sort of a very useful and important application of linear algebra in linear and multilinear regression. So let me also ask you this. In general, are you familiar with multilinear regression, where you have more than one independent variable to fit, or no? So you're just familiar with the linear regression model, is it? Anyway, I'll assume that you don't know what a multiple linear regression model is, and we'll just talk about it. I am not going to talk about the statistics part of it because I don't have that mandate, right? So I'm just going to give you an overview and talk about the how linear algebra tools can be used to solve such problems. Okay, all right. So that will be the next class. So also the other thing that I wanted to say is that I am yet to make up my mind on the third test because by the mandate of the university I have to conduct the third test, but probably instead of, you already had two MCQs, so I think it will be fair to give you a flavor of what the final exam is going to look like. So very likely the third test will be a descriptive type test. Okay, and what I mean by that is, don't be scared, right? If it's a descriptive type test, very likely what it's going to be is that I'll just ask you to solve one problem, and you will have 1 hour. Okay, all right. It will be an open book, open notes thing. I'll give you one problem, and you'll have 1 hour to solve. Okay, there will be partial credits and all that, right? Okay. So that's how the third test. I haven't made up my mind yet, but I think that's the way I'm going to go. I'll have to think a little about this. Remind me this on Monday, and by Monday, I'll be in a position to tell you for sure that how the third test is going to look like. Okay. All right. So, all right. Very good. So we will talk about this more, on least squares and applications of linear algebra and regression problems in the next class. Okay. All right. See you then. Chapter 6. Right now I have just finished chapter 6 from Sheldon Axler's book.